I'd like to thank the organizers very much for the invitation. They've been very patient with me with all my visa issues and so thank you very much. It's really lovely being here. So today I want to tell you about an algebraic cycle associated to a curve. This is not the title I gave you. The title was Certifying Non-Triviality of Ceresa Classes. That probably makes no sense at this point, but I want to slowly introduce the main characters and so on, so hopefully that will make sense. I also know this is the first talk after lunch, so please ask lots of questions. I ask questions to stay awake in a talk, so I totally wouldn't mind if you interrupt me every 5 minutes. So please ask lots of questions. I'd rather go that way. If you don't, I will. Okay, so I want to talk about algebraic cycles associated to curves. So let's give ourselves a nice curve. I wish I spoke right after Tony's wonderful talk, because the idea, it's very much similar in spirit. I'll even use the same notation. So nice means smooth, projective, geometrically integral. So I have a nice curve over some field k. Right now I'll be agnostic about what k is, but later on we'll specialize. I want to embed a curve in its Jacobian, so I'm going to give myself a point. And with this point, you can embed your nice curve inside a larger group that you build out of the curve, right? I'm going to start slowly. People who filter in 5 minutes late would still see familiar stuff on the board, but I want to start slow because I'm going to generalize familiar objects to higher dimensions. So let's recall what this group is. So the Jacobian is a group you build out of points in the curve. So you start with the free abelian group on points on the curve, so zero-dimensional subvarieties. Start with z0 x, but you look at degree 0 subvarieties, degree 0 algebraic cycles, right? Modulo algebraic cycles which are rationally trivial. So just to recall what these are, so this again, like I said, this is the group generalized to higher dimensions. I call this the group of homologically trivial zero cycles. So zero-dimensional cycle. So if you want to be really concrete, over C, I'm just looking at the kernel, look at the free abelian group on points on the curve, and look at the degree map, right? The degree map, also think of the cycle class map to cohomology. So take a linear combination of points, send it to sum of ni. So that's the subgroup of degree 0 cycles or homologically trivial cycles modulo. This by itself is a very large group. It's just a free abelian group we built out of points on the curve to make something more manageable. We quotient out by this very natural subgroup of points that can be deformed to each other along a P1, right? So what is this again? I'm saying things that are very familiar to all of you, but I'm saying it this way so that the generalization to higher dimensions is clear. So the subgroup we mod out by are the divisors of rational functions. So pick your favorite function from x to P1 and identify the fiber above 0 with the fiber above infinity, right? So 2 is this P1, P2, P3, P4, P5. So this subgroup has classes that look like two. I mean, this is a fat point, so things like this. Right. So we've embedded our curve inside this very natural group. So we use this base point to send x to the degree to this degree 0 algebraic cycle, x minus p. Right. So I said I quotient out by this natural subgroup to make something more a group that's more manageable in size, how large is this really? How do we actually get our hands on this group? We all know this is supposed to be a G-dimensional group variety. But it's very hard to get your hands on cycles directly, right? So we study points using the Abel-Jacobi map, right? By using integration. So that's our main tool. So actually I'll erase the title so I can continue this diagram here. Where is the dry erase? I don't want to use the wet. This.
Next to the chalk on the table.
You can.
Oh, I don't want the wet one.
You can use this one then.
Okay, great. Everything I'm going to say today is very much ongoing work. This is work that started at PCMI last year, so we're still in the process of writing it. So this is joint with Jordan Ellenberg, Adam Logan, and Akshay Venkatesh. I'll draw this picture again. Right, so how do we know that this is actually a manageable group? The Abel-Jacobi theorem tells us that in the case of points and curves, so this group, at least over the complex numbers, is something you can understand using integration. Right, so over C, you have you get functionals on the space of holomorphic differentials mod the period lattice, and this is the theorem of Abel and Jacobi, is that this is an isomorphism, right? And this is a group we understand. This is quite a large group, but at least something we can write down, infinitely generated, but it's C to the G mod a lattice. And this map just sends X to the functional that integrates omega along some chosen path from P to X, right? So we want to understand, so this is a very familiar story, so we are trying to understand zero-dimensional cycles on a curve, and the Abel-Jacobi theorem tells us that this is actually a group, quite a manageable group. It's concretely C to the G mod a lattice, and in general, if you want to ask how large is, by the way, I was sitting at the back yesterday and I had a lot of trouble reading stuff at the very bottom. So you should tell me if you can't read anything, if it's not big enough, please complain. So how large is the set of, so this is the G-dimensional group variety. If we ask how large is J of K, of course, this depends on the field K, right? If K is C, for instance, this is a really large group, an infinitely generated group, but the model-way theorem tells us that if K is a number field, if you're over a small field, J of K is the set of rational points on an abelian variety is defined over a number field as finitely generated. Okay, this is all very familiar. What I'm going to do today is talk about generalizations of this. That I very big. Today's goal. Yes. Yes. That's yes.
Question. If you want to talk about the model-way group, are you still happy with the definition that you have over there?
Oh no. Oh, what should I have done?
I don't know. If you can make it work, that's
well, okay.
module structure on it.
Oh yeah. Okay. So this here is the C points of this.
Yeah.
Great. Yes. Okay. People are awake, talking to me. Great. So what I'm describing here is the set of complex points. What did I do? Uh-oh. Can you still hear me? Okay. I'm happy to start this amazing phenomenon. I don't think it's happened before in this conference. So this is the set of complex points of a G-dimensional group variety. But if you start with x over k, this J is actually a nice projective algebraic variety defined over k, and we can talk about its k points. Great, thank you. Keep going. I'm happy to have this. I'm in no rush to get anywhere, so we can take our time, have a nice conversation. So today, the goal is to change the zero. Instead of studying zero-dimensional subvarieties, I'm going to be looking at one-dimensional cycles on the Jacobian. All right, so the main player today, so everything you see on this board is going to get generalized just a bit. So instead of studying zero-dimensional cycles on a curve, I'm going to be studying the group of one-dimensional cycles on the Jacobian. So this is the free abelian group. Instead of zero-dimensional subvarieties, which are points, I'm going to be looking at the free abelian group on one-dimensional subvarieties of J. Okay, I need to be careful about where things are defined over, but I'm going to be looking at subvarieties, say, defined also over K. All right, so made a definition, and I want to give you an example right away, just so we're very concrete. All right, so here's an example / definition. I want to define for you this canonical algebraic cycle associated to a curve, this thing called the Ceresa cycle. It depends on the curve, choice of base point. So it's a certain algebraic cycle that lives in this free abelian group on one-dimensional subvarieties inside the Jacobian. Right, so here's already a question for you. Do you know any one-dimensional subvariety inside J? Yeah, image of the curve. Yes, so we already have one. Actually, we know more than one. We have a copy of the of the curve inside the Jacobian, but you can make a second copy of the curve inside the Jacobian. You can send x to x minus p. You can also send x to p minus x. Right? So you can pull back this cycle by -1. So that's another one-dimensional subvariety. And I'm allowed to take linear combinations. So I'm going to look at the difference. So the Ceresa cycle is the image of the curve in the Jacobian minus its pullback by -1. And if you want a nice sing-song way to remember what this is, you can just sing x minus, but you should put the minus signs in the right places. So this is x minus x upper minus, by which I mean the pullback of x by -1. Okay, this for now seems to forget the dependence on the base point. For what I'm going to do later, it won't matter, but this is just to help you. If there are a few things you need to take away from this talk, one thing is maybe remembering the definition of this Ceresa cycle, x minus, right? All right, so here's this canonical one cycle on a curve. So just like we had, is this the right board? Yes. Okay. Just like we had, in the case of zero cycles on curves, we had all these subgroups, the subgroup of degree 0 cycles, the subgroup of rationally trivial cycles. There's a similar sequence of subgroups inside the Z1 of J. So there's...
Can I ask?
Yes, please.
For the one-dimensional varieties, you consider them irreducible over K, absolutely irreducible? You accept them to be singular?
I think you can take any subvariety. It's a free abelian group on or any kind of subvariety.
Okay.
Mm-hmm.
But defined over K is only the Jacobian, not the cycle.
The cycle's defined over K. You see why in just a bit, because I'm going to make a connection to rational points on the Jacob. Yeah, so this cycle is clearly defined over K, right? X is defined over K, my base points over K, right? So this, so here's a natural filtration on this group, a natural sequence of subgroups on the group of one-dimensional cycles. So you have Z1 of J. You can first ask, what's the analog of the degree 0 divisors, right? So you have the homologically trivial 1 cycles, and I wrote the degree map in that funny way just so that you can see the parallel. So this is the kernel of the map to cohomology, right? So you can take your one-dimensional subvarieties. You can each subvariety has a cycle class. If you want to work over arbitrary fields, like fields of characteristic P, for instance, maybe you want to pick L-adic cohomology. If you don't want to do all of that, if you just want to stick to C, just think of usual singular cohomology. In any case, you can take subvarieties and make a cohomology class out of them. There's the cycle class map. And the homologically trivial cycles are the cycles that go to 0 under the cycle class map. And you should think of this as the analog of the degree 0 divisors. This is it's a higher dimensional analog of the degree 0 divisors you have there. You also have an analog of the rationally trivial divisors. So you have, oh, oops, wrong color. So you also have, so this one here is the dimension of, again, keeping track of the dimension of my subvarieties, and you have the rationally trivial 1 cycles. This is going to be the group generated by cycles that can be deformed to each other along a P1, right? So you pick, now we are in 1 dimension higher, so you pick a 2-dimensional subvariety inside J, you pick some rational function on it, right? And you're going to identify, so the fibers, because this is 2-dimensional, you're fibering it over a curve, the fibers are 1-dimensional, and you get some smooth fibers, some singular fibers, but what you're going to do is identify the fibers above 0 and infinity, get some multiplicities and so on, so similar to what you had here. So if this was C1, and this is a fat C2, C3, C4, C5. And in the subgroup, you have things like 2C1 plus C2 minus C3 minus. Exactly like this, just the higher dimensional analog of rationally trivial cycles that can be deformed to each other along a P1. But in higher dimensions, I left a lot of space here because in higher dimensions, it's potentially another subgroup you can sandwich in between the homologically trivial cycles and the rationally trivial cycles. These are the algebraically trivial cycles. So this is, I say, potentially new. We don't know yet. We'll make a definition. So the definition of this subgroup here is exactly like the rationally trivial cycles, except you replace this P1 by an arbitrary algebraic curve. And yeah, you identify the fibers above any 2 points, right? So in higher dimensions, potentially, there's another subgroup you can sandwich in between. And a curve, this does make sense. Like if you these two coincide, if you try to introduce Z0 alg of X, you look at points that can be deformed to each other along a curve. Any point on a curve can be deformed to any other point on the curve. So these two coincide, right? But in higher dimensions, this is potentially something that sits in between, right? So here's our motivating question. Oh, now I can send this up. Oh, wrong direction. Oh, I still have space. Never mind. Okay. So here's our main question. I've defined a canonical element in here. We want to know how deep in this filtration is this canonical element. How trivial is the Ceresa cycle? The title I submitted was Certifying Non-Triviality of the Ceresa cycle. So the motivating question is how deep in this filtration does the Ceresa cycle live? Is it actually homologically trivial? Is it algebraically trivial? Is it rationally trivial? Right? Okay, let me send this also up. All right, so actually there's a reason I took the difference of x with x minus, so I'm going to, here's a fact. I don't need this anymore. There's a reason I took the difference of x and x minus and not x plus x plus. Taking the difference makes the Ceresa cycle homologically trivial. So the Ceresa cycle already lives one step deeper. And the reason is if you look at so the difference of x and x minus is they differ by pullback by -1. You can ask, what does pullback by -1 do at the level of cohomology? If you take these two cycles, push them into cohomology and ask what happens here, turns out they don't change. Right, so pulling back by -1 acts trivially on h2g minus 2. If you think about this, this is really the 2g minus 2 wedge power of h1. On h1's like the Tate module, and we know -1 in multiplying by -1 on the Jacobian induces multiplying by -1 on the Tate module, right? So x and x minus go to the same thing here, their difference goes to 0. So x minus is already homologically trivial. So the refined question is, okay, does it now go even deeper in the filtration? So is x minus non-trivial in the quotient of homologically trivial cycles modulo the group of algebraically trivial cycles. So this group has a name. This is called the Griffiths group. In this quotient, I can really forget this dependence on the base point. So if you change the base point p, you don't change the algebraic equivalence class. So really, I'm justified in forgetting the base point. It's translating by a point on the Jacobian. So x minus is really well defined. Independent of the base point. All right. So, any questions so far in the definition? Oh. All right. So let me start telling you what's known about the Ceresa cycle. So what's known? So if you see a definition about something associated to a curve, maybe you want to understand what it is for your favorite class of curves. My favorite class of curves are the class of hyperelliptic curves. You can do very concrete computations. You can ask, what can you say about the Ceresa cycle of a hyperelliptic curve? So the case of a hyperelliptic curve, the Ceresa cycle is not so interesting. So if you take a hyperelliptic curve and you choose a y-stress point, it turns out that this Ceresa cycle is actually 0, even before you quotient out by any subgroup. It's 0 in this group. Does anyone see why? So yeah, -1 on the Jacobian doesn't come out of nowhere. It comes from, it's induced by the hyperelliptic involution, right? So you have this, if you use your y-stress point to embed the curve in the Jacobians, it's a fixed point for the hyperelliptic involution. This x minus -1 upper star x just happens to be the curve itself. It's the hyperelliptic, this diagram commutes, it's, you get back x, so the difference is actually 0 on the nose. So for hyperelliptic curves, the Ceresa cycle is not that interesting. Great question. This was Clemens's question for a long time. These were the only class of curves where you could see that the Ceresa cycle was 0 on the nose. He even believed that the Ceresa cycle, he posed this as the question, are hyperelliptic curves the only curves where the Ceresa cycle is torsion? The answer is no. So of the last 5 years, there have been several examples, some due to my collaborators and myself, like Dean Bisogno, Wan and Lee, Dan and Litt, and now more recently, last year, there are whole families of curves, non-hyperelliptic curves with torsion Ceresa cycle. Yeah. And all of those curves are rather special. They're all curves with extra automorphisms, and the automorphisms play a key role in showing this. Okay, maybe I should write this, because if I was giving a different talk, there are several talks I can give on the Ceresa cycle, but there is, can ask for what class of curves is CXP torsion. Are these obvious examples the only class of examples? The answer is no. I can give you a very explicit example. If you look at the Fricke-McBeath curve, genus 7 Hurwitz curve, it's defined over Q zeta 7. It has torsion Ceresa cycle. 0 on the nose, I still don't know, but there are curves with torsion Ceresa cycle that are not hyperelliptic. All right. Great. Great questions. Please keep asking. So this, the cycle is called the Ceresa cycle because Ceresa studied this in his something about standing here. Maybe step on some wires. Okay, I'll be careful. In his 1983 thesis, Ceresa showed that after hyperelliptic curves, you can ask what's the next most interesting class of curves. If you're only allowed to ask this question once, you should ask what happens to the generic curve, right? That's by far the most interesting curve. And we'll ask about the generic curve of genus at least 3, because we know those are non-hyperelliptic. And what Ceresa showed is, in this case, the Ceresa cycle has infinite order. The Ceresa cycle of the generic curve has infinite order in the Griffiths group. Okay, so concretely, if you're asking how deep in this filtration is the Ceresa cycle, not only is it not in the subgroup of algebraically trivial cycles, no multiple of it lands in the subgroup of algebraically trivial cycles. Yes, Drew?
What do you mean the generic curve with a rational point? You're assuming it's a rational point.
Oh, you can, great question, be sloppy. You can, this class here doesn't depend on the choice of base point. These are going mod algebraically trivial cycles, but yeah.
Weighted finite generated, still Mardel-Weir theorem holds if you finite generation.
Yes.
So now it's called Mardel-Weir one neuron theorem.
Okay. Okay, you're talking about finite generation of this group. I'll get to this in just a bit, but like I think Drew's question was do I mean a generic pointed curve of genus at least 3? I don't think you need a generic. I mean, this is over the complex numbers. This is an argument.
Actually, let me translate this question. How I understood it. If there is a curve x over q bar such that the Ceresa cycle it has infinite order.
Yeah. Okay. You could definitely say that. Yes. The generic curve over the function field. If you want to be precise, we can say generic curve over the function field of Mg has infinite order Ceresa cycle in the Griffiths group. All right. So this is a curve, but maybe again this is not satisfying. Nobody's seen the generic curve. You can't. This is not a curve you can write down. And I know many people here like actual equations for curves. So the first explicit example of a curve over a number field. I think this also appeared in 1983, but of course follows Ceresa's result as a result of Bruno Harris, and he studied the Ceresa cycle for the Fermat quartic. So x to the 4 plus y to the 4 equals z to the 4. So he showed that the Ceresa cycle is non-zero in the Griffiths group. All right. I won't say what I just orally described why he was what he did. So cycles themselves are very hard to get your hands on explicitly. What we do is instead map them into groups we can understand, right? So the way to understand devices and curves is using the Abel-Jacobi map, right? By integrating devices against cycles. So you can do a similar thing here. There's a version of the Abel-Jacobi map, and what Bruno Harris did was study the Abel-Jacobi image of the Ceresa cycle, and he was able to show that he actually computed a certain period integral in the Fermat quartic, and he was able to approximate, it's a 2-page paper with an actual integral that shows up. And he was able to numerically approximate this integral, see that it was not an integer, right? So that was enough to show that the Ceresa cycle is non-zero. If you actually wanted to know if it was infinite order, that requires knowing if this period integral is irrational. And irrationality of periods, like that's quite a difficult question. So this technique, his technique was good enough to show the Ceresa cycle is non-zero for the Fermat quartic. And then Bloch, this is historically actually quite an important example, because Bloch studied the Fermat quartic again, and using an Eladic version of the Abel-Jacobi map, he was able to show that for the Fermat quartic, the Ceresa cycle has infinite order in the Griffiths group. Right? And this is again very special curve, the Fermat quartic. We really know quite a lot about its Jacobian, and since then there's been a search for other examples where maybe you can adapt either of these techniques. So extending work of Bloch, Bruno-Harris, using, again, Alaric, Abel-Jacobi maps, like these sorts. There are period integrals. There have been other curves, but they're all rather special. So you have things like low-degree Fermat curves, quotients, and like genus 3 curves that embed in the triple product of elliptic curves is Yap-Top. I don't see him. He's somewhere in the audience.
Excuse me. That means that
Yeah.
in all of your examples, the Jacobian has complex multiplication.
Has complex multiplication, and that's actually quite important in these arguments. They show up. It's crucially used in these arguments. So there's Yap-Top's thesis in 1989. There's work of Kimura, 2000. These very special curves. So curves like with CM Jacobian, and so on, and curves with lots of additional correspondences, and those actually play a role in the argument, right? But if you think about it, Ceresa tells you, Ceresa's original result, where did I write it? Tells you that the generic curve has infinite order Ceresa cycle, right? So this actually suggests there should be lots of examples out there with infinite order Ceresa cycle. Turns out it's very hard to verify by hand. So the first theorem, maybe I should bring them all down. No, how do I do this? Like Yuri's observations, very important. These are all very special. They have lots of automorphisms. They have CM Jacobians, extra correspondences. And all of those, people really use all of these to show that the Ceresa cycle has infinite order. But if, like in Tony's talk, if you just generated a random equation out of hand, if you want to know what can you say about the Ceresa cycle of a random curve? Up to now, there wasn't a technique to understand this, but the result I'm going to present today, I guess I needn't have erased this, is to show you that there are lots of examples out there. For instance, we have 200,000 order new examples of curves over Q with infinite order Ceresa class. But not modulo algebraic equivalence, but modulo rational equivalence. Let me just say what these are, just a second. Sorry, this is not what I meant to write. So this seems like a random number, but where it comes from is we have an algorithm. We ran our code. We have Magma code that samples. So, oops, to rearrange things last minute. So theorem, so if we have, so this is, again, joint with Einberg. Having a rational point is not important for what we do. So we have an algorithm that certifies that the Ceresa cycle has infinite order in this quotient of group of homologically trivial cycles mod rationally trivial cycles, and it's an algorithm that certifies that the Ceresa cycle has infinite order in this quotient in this Chow group, and either it does that or it does not terminate. And what we did, so these examples, where do these come from? These we ran our algorithm in Magma on low height smooth plane quartex. So randomly generate a genus 3 curve over Q. So example, when you ask how many these are, you can understand smooth plane quartex that are invariants to study isomorphism classes. We ran our code on height 1 smooth plane quartex. So this just means concretely, just like in Tony's talk, you generate a random degree 4 equation of a plane curve, and you sample the coefficients in this bucket of -1, 0, 1, right? And sieve out smooth ones. In almost every single example of these curves, we were able to certify the Ceresa class had infinite order. The algorithm failed to terminate in only 102 cases. So in all other examples, in the remaining ones, we were able to produce a certificate that the Ceresa cycle had infinite order, right? And like, yeah, most of them don't have points, for instance. I mean, just generate random equations. Any questions? Yes, Drew. Fail to terminate means we don't know. Maybe the Ceresa cycle is torsion, maybe it's not, but yeah.
But it failed to terminate because you didn't wait long enough, or it went in an infinite loop or something?
We didn't wait long enough. Maybe if we keep searching longer, maybe we produce a certificate, or maybe we still can't tell. So I'll tell you a little bit more about what this algorithm is, and that'll become clear.
Can you say anything about what happens in the Griffith loop for these examples?
Amazing question. Thank you. I have this technique, this work with Adam Logan, Ellen Bergen, Akshay Venkatesh cannot tell you what happens in the Griffiths group. This is really for something in the Chow group. But you can use p-adic integration to study non-triviality in the Griffiths group. And where am I? Sorry, just a second. So let me state this. I will not get to talk about this in today's talk, but I also have, the question now was, what about non-triviality in the Griffiths group? So non-triviality mod algebraic equivalence. So this have ongoing joint work with Amnon Besser. This, after this conference, I have to go back. I have more coding to do, just like Tony. And what you can do is, so this is an Aladic method. We use the Aladic Abel-Jacobi image. And if you instead study the p-adic Abel-Jacobi image, that gives you a certain functional on differential forms that you can compute using Coleman integration. And so this functional takes as input 3 differential forms of the second kind. And if you ask what it does to 3 holomorphic forms, it produces a number, it does some magic. It takes 3 differential forms, outputs a number. If you get a non-zero number, then it means your cycle is non-zero in the Griffiths group. Can be used to certify but I will not talk about this today. I'm happy to chat later. All right. Okay. Which board was I at? This needs to go. Oh, this needs to go all the way up. This is so confusing. Maybe I have other boards to write on. I'm just very confused. Maybe stick to the middle board. Okay, maybe at this point you have a very natural question, like why do you care about certifying non-triviality of the Ceresa cycle? Why care how non-trivial the Ceresa cycle is? And there's good motivation. Yeah. So this is why I spent some time writing down the model way theorem and rational points on the Jacobian. So more motivation for why care. So it's not even like Yuri points out, it's not even clear if there are homologically trivial cycles that are not algebraically trivial. The Ceresa cycle was one of the first examples that showed that these two equivalence relations are different. But there's also number theoretic interest in like number theoretic reasons why you should care about the Ceresa cycle. So here's an analogy. I think like most people in the audience care about rational points on abelian varieties, the model way, computing the model way group, and so on. And you should think of the Griffiths group as a higher dimensional analog, the Chow group and the Griffiths group as a higher dimensional analog of rational points in the Jacobian. This is why I was looking at cycles defined over K, so I can make this analogy. And there are very interesting conjectures. So for rational points in the Jacobian, the model way theorem tells us the group is finite. This is a finitely generated abelian group, and moreover, its rank is controlled by the order of vanishing of an L function, right? So we have the BSD conjectures, and there's an analogous conjecture for the Griffiths group. If you're over an arbitrary field, like I pointed out, over the complex numbers, there are lots of examples due to Mumford, Voisin, and others that show that this Griffiths group can be quite large. It need not be finitely generated over a large field, but the conjecture due to Bailenson and Bloch didn't call it a conjecture, it's Bloch's recurring fantasy. If you look at his paper, he calls something a recurring fantasy and calls something else the son of a recurring fantasy. It's really fun to read. There's a high dimensional generalization of the BSD conjectures that predict that these groups are finitely generated, and moreover, the rank is controlled by the order of vanishing of an L function if you're over a number field. So if X is, I'm stating a special case of the Bailenson Bloch conjectures that are relevant for in this setting. Then the rank of this group, someone's sneezing, is equal to the order of vanishing of the L function at the central point. Which L function? The L function associated to a certain Galois representation. In this case, the relevant Galois representation is H2G minus 3 of the Jacobian at the central point. And I must say that in higher dimensions, we don't even know the finite generation of this group, right? It's quite a lot that's mysterious in higher dimensions. But in some cases, this Galois representation maybe is something very special, and you can compute the L function by hand. you should ask Yaptop for examples. I think in his thesis, they were actually able to compute both sides of this equation. So if you know you have an L function where that vanishes at the central point, you want some way of producing an algebraic cycle. Yeah, this is just an analogy, but one way of thinking of the Ceresa cycle is it's some kind of natural cycle that's very likely to have infinite order, so some kind of analog of a Heegner point, right? So, if you know for other reasons that, am I already out of time? Wow, okay. I took a 20-minute talk and tried to put in a 50-minute talk. Okay, so, all right, so this is good reason to study the Ceresa cycle. So I stated our result. Maybe I should just very briefly say, can I take an extra 2-3 minutes just to say what the algorithm is, and then I can stop. So the key tool here is okay, so we want to show that a certain algebraic cycle has infinite order. It's hard to study cycles on their own, right? So what we study is cycle classes. So you can map. So the idea is in our proof. So you can map. There's a cycle class map. You don't want to take the usual cycle class map that will send homologically trivial cycles to 0, but there's a refined cycle class map that maps to H1, just like in Tony's talk, a Galois homology class in H1. And it's one mantra to remember: cycles are hard, but cycle classes are easier. And what you can do is show that the cycle class, the Eladic cycle class, is non-trivial. And for this, certify the Ceresa class. Has infinite order. And for this, you can produce both lower bounds and upper bounds on the order of this Ceresa class. Okay, so I hit something on the board. Maybe I should have written more. So you can produce an upper bound, computable upper bound, n on mu x, and you also have lower bounds on the order of the Ceresa class. And the algorithm, the lower bound comes from taking auxiliary primes of good reduction. So I want to answer the questions I got at the beginning. So the upper bound, it's just an argument using weights. So instead of bounding the order of this class, you bound the order of the maximal torsion order in this group. It's just an exercise in Galois homology. What's the maximal torsion order of an element in here that you can write down? It has to come from invariance in M. If you're looking at L torsion, that comes from invariance in M mod Ln, and you can figure out exactly when this happens. So this is something that's computable from the characteristic polynomial of Frobenius, for instance. But the lower bound is much more interesting, and this really uses the fact that if you take a random curve, it's likely to not be special, not be CM, not have extra correspondences. But if you reduce the curve mod P, it's like a Tony's talk, reduction mod P is what comes to the rescue. You have extra correspondences. You have the Frobenius, right? And you can take the Ceresa class, map it under a certain homomorphism, and produce a point in the Jacobian of the curve over the finite field. And here's a very canonical point. Right? Forget everything else I've said in the talk. Maybe you don't care about this. You only care about points in Jacobians. Look at this very natural point in the Jacobian. Sum all the rational points on the curve over Fp. Take the canonical divisor. Right? Okay, I want to combine them to make a degree 0, so weight them appropriately. This is a very natural point on the Jacobian of a curve over a finite field. And you can ask, is it non-trivial? What's its order? Right? And the algorithm just says, compute this upper bound n and these n sub p's for all p less than some chosen bound. If you find even one n sub p that does not divide n, then you know the Ceresa cycle has infinite order. If the Ceresa cycle has torsion, its torsion order has to divide this n, but there are also lower bounds on the order coming from reduction mod p. So if you find even one p where n sub p doesn't divide n, you know the Ceresa cycle is infinite order. Very sorry, I have no idea how long I've been speaking. I'll stop here. No questions.
Thank you very much. Is there any more questions or comments? Yeah, please, Drew. Oh, no, wait, I have to give you the micro.
So 2 quick questions. First, what do you think is happens with those 102? Do you think?
Oh, excellent. I have to go do some coding and write down my this p-adic algorithm and see what happens. I think even that, you fix some precision. I have to test it against this other algorithm, see what it says. It's unclear what's happening. But I will point out in all of those other 102 examples, they were all special curves. They're all curves that had additional automorphisms, for instance. Maybe some of them can be ruled out if we went up to larger p. Adam Logan did the coding. I think he changed p from 50 to 100. We still have these 102. I'll have to test it against this p-adic integration algorithm, see if we can rule out some more. But it's unclear. It's very difficult to show if the Ceresa cycle is actually torsion. If you had, in some cases, you can play games with automorphisms and show that the Ceresa cycle is trivial. That's what we did in these Fricke-McBeat type examples. But there is no general technique for certifying the Ceresa cycle is torsion.
And then my other question is, what do you think is true in the Griffiths group for these 254,602 where you know it has
I mean, I have to do some, ask me again in a few months, Drew.
So I remember some joint work of Robin de Jong and Farbot Chocrier, where they were computing a height in a certain sense of the Ceresa cycle on the compactification of moduli space of genus G curves. So are you using this somewhere?
We're not computing heights, but there is just like the height of a rational point. I guess what they're computing is this height for high dimension cycles. I have no idea what they actually do. But like if you compute the height and you find it's non-zero, that's another way to certify it. Something has infinite order. Yeah, we're not using that.
More questions or comments?
For the class of the Ceresa cycle, is that dependent on base? Does it behave well under base field extension?
Base? The Ceresa class?
Yeah.
I guess so. Like you can play. I mean, you look at the base extension of the curve. I think you can draw commutative diagrams.
You can just base extend.
If you're just interested in whether it's torsion or not torsion, yes, certainly that's a geometric property. Whether the Ceresa cycle is torsion, Ceresa class is torsion. Yes.
But was it 0 or not?
Huh? 0 or not? You can't. That's a final question. Yeah. You can't make base extensions. Maybe you have something that's torsion that becomes 0. Yeah. Whether it's infinite order or not is something that you can study after making base extensions.
I'm definitely convinced that this is awesome, the Ceresa cycle, but I was just curious, like, is this the sort of motivation that Ceresa had when, they were
for studying the Ceresa cycle originally, I don't know. Bailenson and Bloch made their conjectures after the results of the Ceresa cycle came out. So I don't know. I don't know if he secretly had this in mind and didn't know. But Bloch, this exam, the Ceresa cycle of the Fermat quartic is historically quite important. The formulation of these conjectures. Bloch was also able to compute the order of vanishing of the relevant L function, and he was able to show it vanished at the central point. So okay, hey, this is consistent. This is good. But based on one example, he didn't want to call it a conjecture. He called it a recurring fantasy. But yeah, Yaptop has more examples. You can ask him.
More questions or comments? Okay, if not, we thank Padmavathi.